Wait a minute. Good morning, everybody. This is another installment of the Rocket Minute with Jason Wampler. That's me. I'm your host. Um, I'm staring at Paxton, who's laying down in a ray of sunlight, and I'm staring at Valencia, who is in heat right now, and she's acting ridiculous. She's cooing and calling through an open window, looking for a boyfriend. I found out something interesting. I know this is not related to rockets. Paxton is not a girl cat. Paxton is a boy, which is confusing because he's just kind of a soft, kind of wimpy boy. He likes to fight, but I just thought all male cats were a little bit rougher than that. But Paxton is a boy. He has what men have that are inherent to the male anatomy. I had to check because he's still young, but him and Valencia are starting to mess around, and I'm getting concerned. I don't want more cats to have to feed and deal with. You know what I mean. Anyway, let me straighten this out as I am constant endeavor to straighten out the production value of these videos. Wow, we're still really working at it on this one. Anyway, okay. Let me put the light on as well. No, that's too high. There you go. It's another shot. All right. So anyway, it's still so high. Boy, I tell you what, art is 1% inspiration, 99% perspiration, and I have the nerve to call this art. So what we're going to talk about today, because I attempted to shoot this video before, the process of shooting videos on your smartphone. You know, even the best smartphone in the world has a finite memory. So when you shoot videos, that's what I'm learning, you load it onto a platform, develop a collection, like a playlist on YouTube. You let YouTube store your videos, but you get them off of your phone. You keep freeing up space. So now every time I shoot a short and a video, I'm going to free up space and clean my phone so that, because my phone has a very small fuel tank, as the saying goes, for memory and storage of videos. I try to review videos before I upload them to YouTube. I don't talk about religion, politics, sex, drugs, rock and roll, or weapons, and nothing about any type of violence. No personal opinions for or against any social movement. I'm a U.S. citizen. I'm one of Jehovah's Witnesses, so it means I'm practicing Christianity. The Bible is my holy book. Again, I'm not trying to talk about religion, but I'm trying to tell you about who I am. I don't smoke. I don't drink. I don't do drugs. I'm still single. I'm not married. A nice girl has not come along just yet. But like I said, I have the 2 cats for companionship. Of course, I associate at weekly religious meetings. So that's my life story. I don't believe in violence. I don't like arguing with people. So the reason I'm saying this is kind of to give you an idea of my character. I used to be a mechanic. I was a mechanic for 37 years. And I got to tell you, I'm watching these horror stories of other mechanics and what they have to deal with, these recent posts and videos in the form of shorts and videos on YouTube, which is a wonderful, wonderful platform. I praise YouTube all day long. And they're just coming up on old familiar territory. I got to scratch my head and wonder why these mechanics have the love and patience they do. And I remember that I was in the same business for 37 years. I had been working on cars since I was 15 years old. And what can I say? Things haven't changed. They've only gotten worse. And I have to tell you, engineers and manufacturers of cars, they've gone from irritating to mildly stupid to now just full-blown retarded alcoholic cowards. Scotty Kilmer is right. The whole business is just going down the tubes. A shout out to Scotty Kilmer. Scotty, you're my hero. You keep standing up to the big guys and keep fighting them dragons. Don't be afraid. Don't back down from a fight. Well, I am no longer an automotive mechanic. I'm not a shop owner. I'm an aerospace engineer. I've been an aerospace engineer for a very, very long time. I don't know why I decided to vector off that career path, but here I am at 53 years old. I have decided to be very true to my nature, 100%. Let's talk about rocketry. I wanted to share with you a fact. Probably going to end up falling over. Why did I do that? This chair is just beyond wonderful. Why they, people, products these days are just made to move too much. They're too flimsy and they have too many different movements. I need something that just fixed parts and maybe moves in one direction or another. We talked about this motor system. This is for my level 2 rocket. This, as you can see, is roughly 38 millimeters in diameter. Let's see. This, I have spent a lot of time on this system. Now that I've got the camera set up properly and I want you to see inside that. I made a mistake on this fitting. This is an actual 1 3/4 inch or 2 inch plumbing fitting. I square sanded everything up with a belt sander and a 3/4 inch grinder, so these two white surfaces are level. That's important because this is going to fit in the tail end of the rocket. I want to explain this in detail. This is extruded seamless 6061 aluminum T-6061 extruded seamless aluminum tube. I got this on a stroke of good luck. I was searching for free stuff on Craigslist, which is a good idea because you can get pretty much anything and everything you need as far as materials are concerned on Craigslist. The fitting, of course, I got either from Lowe's Hardware or Home Depot. I'm going to start shooting videos at Home Depot once the weather clears up. We've had a really wet winter in California. It's dry for 3 years, and then we catch up in 1 year, and it's nonstop raining. So I'm more inclined to work indoors than I am outside. I rounded this fitting and I leveled it off. I completely sanded and cleaned up the body tube. There is kind of a gouge there. I don't know if you can see it. This is the motor. This is what's going to be called a SERMS motor, a HASERMS, HA-SURMS. That stands for high altitude single-use rebuildable motor system. That's my invention. It's not necessarily an SSTO motor. I'm going to obey the rules of 3. And I might as well just go ahead and explain that. The rules of 3 for coring a rocket. And by the way, you really, for something this big, you want what's called a core burner. Or if you want to get exotic and you're able to develop a mold, a packing mold, you can create what's called a star burner. But I like core burners. And core burners, for lack of a better word, is a rocket motor. I'm going to go ahead and draw a picture of it. A rocket motor where the center of the motor, let's see, that's the casing itself, right here, you can see that my writing is terrible. This is right here. My pen is pointing. That's the center of the rocket motor. That's called the combustion chamber. This area here, I might as well just put some X's in there to show solidity and put some dots there and everything. I'm not an illustrator. I'm a fabricator, designer, and builder. This solid area here, you can see on there, that solid area there, that is the fuel grain. This outer casing is phenolic. Phenolic is an insulator. It has what I call single-use structural integrity, but it's not reusable. Once you use phenolic sleeve in a high-powered rocket motor application, that's it. You're done with it. Throw it out. That also includes it's black carbon relative, which is called Bakelite or Garolite XX. Look that stuff up. Garolite, Garolite, and then 2 X's afterward. It's also known as Bakelite, Bakelite. They're both the same thing, 2 names for the same thing. You can get that stuff off of McMaster-Carr online, but they don't manufacture things to your specifications or the specifications of a 38 millimeter rocket, which is you want to get in the upper end of a J rocket for level 2 certification. And again, 38 millimeters, that is that diameter. I know I kind of bounced it all over the place. Let me get back to the rule of threes, though, because I keep derailing my train of thought. This core right here, I get a pointer. Man, my hands are dry, and I just got an ink spot on my shirt. This core right here is an empty space. That's called the combustion chamber. I'm going to draw some better illustrations, but basically you count this entire total inner diameter in the phenolic sleeve that goes inside the aluminum body tube of the motor itself. 1, 2, 3 even sections. Now the rule of threes for a conservative high-power rocket motor designer is just this. The left side of the rocket, if you're looking at it from the business end where the thrusting exhaust comes out, 1/3 of the left side, 1/3 of the right side, and 1/3 of the middle are fuel grain, empty space, and fuel grain. That's the rule of threes. So if you're going to be making fuel grains or solid fuel pellets, a safe and conservative way with safe and conservative fuel like magnesium, 20% magnesium, 20% potassium nitrate. 20% magnesium, 20% epoxy, 60% potassium nitrate, everything ground up in air float and mixed and cast and then dried and machined very, very slowly using water because nothing is water soluble. Be very careful. I'll show you. Well, I shouldn't show you how to do that. The core, the combustion chamber, the empty space. These spaces right here. This empty space is going to have a phenolic sleeve in it to insulate the heat for the outer tube, which is the T6061 extruded seamless aluminum. The core itself is going to be designed based on the rule of three, that 1/3, 33 1/3% on the left side of this core is going to be fuel grain. 33 1/3% moving over to the right is going to be that empty space. 33 1/3 is going to be the right side fuel grain. So the combustion chamber is going to take up a total of 33 1/3% of the total diameter of the fuel grain itself, inside or in between the internal diameter of the insulating phenolic or Garolite XX, aka Bakelite sleeve. That's the rule of threes for that. Now I'm going to draw another illustration. You guys are going to have to be patient. We're at the 13-minute mark. But I said I was going to be, this is going to be an instructional series, and that's what it needs to be. So I'm going to do this. The rule of threes applies to nozzle design as well. And you have three main sections to a nozzle. You want to develop a four-square side of the nozzle barrel. In my opinion, needs to be a little over 4 square. It needs to be a little bit longer than the diameter, probably by about 10 to 15%. 10% longer than the diameter. So the length of the barrel, the nozzle barrel, is 10% longer than the width of the barrel. However, I want to draw a profile. Again, you're developing a conservative motor because if you're designing and building your own motors, which is one of the most economically sound things you can do, because commercially made motors, you need them to participate in launch events and get your level certification. But I got to tell you, the bigger stuff is going to drain your bank account. So this is helpful information. It's not illegal, but we're going to talk about the legalities, including fire marshal permit and LEUPs, low explosive users permit. So you've got to be legal. You've got to be in compliance with all the local, state, and federal laws if you're going to do this. Now, people do it, and they do it, and it turns out to be a profitable business venture for them, and they end up serving the U.S. government, becoming U.S. government contractors, and actually benefiting the U.S. government. A couple of people who have gotten into model rocketry that I can think of, like Cesaroni Technologies and the Gates brothers, I believe, are now U.S. government contractors, defense contractors. especially Cicerone. They're going international. The last I saw, Cicerone Technologies had 2 international offices. They used to manufacture rocket motors for hobby enthusiasts, model rocketeers, and high power model rockets. Now they're government contractors. So the U.S. government, if they see you're doing things in good spirit for the effort of furthering your knowledge, education, experience, etc., we're not going to be red flagged as a community of rocketeers. Back to the nozzle design, the rule of threes. 1, 2, 3, 45 degrees, and then we have 30 degrees. Oh my God, I'm used to. Anyway, kind of new at this. I'm gonna get a chalkboard and set up this Julie. Now I want you to see this, and of course it's backwards, so I gotta write backwards. So leave numbers out of it. This is a nozzle. This is the internal diameter of a nozzle. If you cut that barrel in half lengthwise, this is the entry point of the nozzle. It's always 45 degrees, so 22.5 degrees on both sides, all inclusive. And that's 45 degrees. Now it could be a 90-degree angle where it's 45 degrees on both sides, all inclusive. I have to clear that up. I apologize if that is misinformation, but I'm just trying to think. Well, I know the exit nozzle is 30 degrees. I know the entrance nozzle is 45. I know that both angles are 22.5 degrees. That's the entrance side of the nozzle facing the combustion chamber, and the fuel grain sealed inside the motor itself. This second section, basically barely 1/3 the overall length of the nozzle barrel. That is 1/3 the length of the nozzle barrel itself. It is also 1/3 the diameter of the total fuel grain. That is the space the fuel grain takes up on the inside of the insulating phenolic sleeve, inside the T6061 extruded seamless aluminum motor tube, which also needs to be either anodized or heat treated. We'll talk about that later. And this last 1/3 section, of course, is the exit nozzle. This is the business end. This is where exhaust gases come out, provide thrust, and lift the rocket up off the pad. That is 30 degrees, and I'm absolutely positive about that. 30 degrees is 15 degrees on either side, all inclusive. So 1/3, 1/3, 1/3, 45 degrees, 22.5 degrees in all inclusive angle on both sides, 30 degrees, 15 degrees exit nozzle angle, 30 degrees all inclusive. 1/3, 1/3, 1/3. Now this is a 4-square barrel. It's a barrel, but it's as tall as it is wide, but it's a little over 5 or 10%. I'd say 5 or 10% longer in length than it is wide. So the length is 10% longer than the total diameter. Radius is halfway point. Diameter is full length from side to side. In consideration of the actual space that the solid fuel grain takes up, not the outer diameter of the motor itself, which includes 2 times the wall thickness of the actual aluminum casing itself. You don't want to include that. That doesn't count. That's for structural strength, but that is not a consideration of the volume of the solid fuel. So don't make that mistake when you're designing your motor. So the rule of threes is applied. So 1/3 entrance nozzle, 1/3 actual throat, 1/3 exit nozzle. That's for a basic conservative model rocket motor nozzle. The material you want to consider using phenolic, but phenolic again is single use. It's ablative. You cannot maintain the throat diameter, which is critical for the total impulse of your rocket motor, which is burn time times pressure and even volume exiting the nozzle, which provides thrust. What are they called? Oh my goodness. So burn time times thrust equals total impulse of the motor itself in Newton pounds. Now, you have to test your motor, and we're going to talk about the 4 different stages of actual experimental motor testing. But I do want to say this. Number one, you need to know what you're doing, and you need to do study and research before you attempt anything and watch my videos. The other thing is, too, you need to absolutely positively be in an area that is safe and legal to do so, where you're away from anything and everything combustible. You're out of sight from other people, because if you start testing rocket motors and you mention the word rocket, you tend to freak people out. People who don't have any exposure to rockets or rocket motors or high-powered rocket model rocketry, it's a subject that can spook them. It's like developing firearms or making explosives. You're not doing anything destructive. Of course, you're not engaging in any illegal activities, but people are afraid of what they don't understand, so be careful. My guess is leave the state of California, go to Black Rock, Nevada, because the playa dust is not combustible. Nothing in Black Rock is going to catch fire. That's why they have so many rocket events there. But that's the rule of threes. 3 sections, a 4 square barrel, 3 sections: entrance, throat, exit, 1, 2, 3, plus 10% length over width. And then, of course, the throat is 1, 2, 3, same as the fuel grain, 1, 2, 3. That's a very, very stable conservative design. Okay, so that's that. So let's talk about that. I want to talk to you very, very quickly about the several stages of motor testing. Number one, first test, and I have to emphasize this with a great deal of emphasis, and this is very, very important. Listen very carefully. Number one, do not, and I repeat, do not to attempt to experiment with solid fuel or solid propellant formulations. Do not do that. Under any circumstances, do not allow yourself, now I'm restyling my hair again to increase production value, and put another coat of paint on that barn. Do not experiment with rocket fuel propellants. No matter how smart you think you are not a chemical engineer. Don't do it. You're going to hurt yourself. You may even end up killing yourself, maiming yourself, disfiguring yourself, or losing a finger or a limb. A rocket motor this size could possibly be something like as much as a J390 or a J400. 400 newton meters, 400 Nm newtons of total impulse of burn time times the pressure and volume exiting the nozzle equals a tremendous amount of force. A J motor like this also could go in a military, a tactical missile on an aircraft, on a military aircraft in the Air Force. My dad, Sam Armstrong, was telling me a story about how he was on a chaff boat, a misinformation boat, where they launched chaff missiles that threw off radar. Him and his buddy, they were working on gauged instrumentation. He's working with missiles, so he's passed that on to me hereditarily. He says they both got in the blast path of what was the equivalent of a J-powered chaff rocket. It had bits and pieces of aluminum in it that disrupts the enemy's radar. Basically, a J-powder motor is this same size motor. My hand is there for perspective. Here's my face. That is roughly 38 millimeters. He said it gave him second-degree burns on his chest after it completely tore off the shirt off his upper body and knocked the wind out of him, blew him backwards by several feet. And that includes what happened to his buddy as well, which is the same thing. Don't screw around with trying to formulate your own rocket propellant. Go with established formulas, and I have several formulas for you for that. But I have to tell you, I'm disclaiming any liability. If you screw up, it is not my fault. It is yours. I'm going to be very, very, very specific and careful. I don't even think I'm going to be shooting videos with regards to propellant formulas until I feel I'm dealing with a more mature audience. And I got to build you up. Careful handling. You're not a chemical engineer. I'm not a chemical engineer. I'm a mechanical engineer. I'm an electrical engineer. I'm an aerospace and automotive engineer. I am not a chemical engineer. I don't like chemical engineering. I don't like explosives. I don't like blowing things up. I like creating fuel. I love rockets. I love launching and flying rockets. It is my passion. I don't like things that blow up and hurt people. I'm a non-violent individual. So do not do that. So we've discussed the basic rule of threes with these two pieces of Day-Glo green tabs. Now let's discuss the overall length of the rocket. Proportionally, you don't want to exceed a 6-to-1 ratio, 6 times the length being 6 times the width of the rocket. Honest to goodness truth is you can go up to 8-to-1. And let me put this down on paper so you have a visual aid. 8-to-1 or 6-to-1 is radical conservative. And here we go. Now we're already talking about politics. I swear to God. We're having fun yet. Okay, look. 8-to-1 length. 8-to-1 length is close to the space shuttle boosters themselves. Those are called SRBs. They're ammonium perchlorate, aluminum, iron oxide, and a rubberized, high pressure, high temperature type of polymerized epoxy binder with other burn rate modifiers. Those are AP boosters. They provided 4 million pounds of thrust each. The individual orbiting motors, the liquid oxygen motors with kerosene, provided 2 million pounds of thrust each, which indicates to me that solid fuel rocket motors take up more space. They're much, much more basic than liquid fuel rocket motors. I'm not really going to get into liquid fuel rocket motors probably about another 5 or 10 years until I get some other experience under my belt. These are the ratios, and it's kind of like glare. Maybe I should take that off. Shucks. See that? It's backwards, and that doesn't make any sense now, does it? I keep forgetting it's going to do that. A radical rocket motor design, which is mine, is a roughly 8-to-1, 8 segments, 8 squares, or 8 even segments of division along the entire length of what the fuel grain is going to take up as far as the internal volume with the sleeving around the grains of this particular tube of aluminum, which constitutes the motor housing. This motor tube, by the way, has not been heat treated. That was my mistake. We'll talk about that in a second. 8-to-1 is 8 times the length versus the width. So you take the width, which is the diameter of the rocket, multiply it by 8. That is the length of the rocket motor. So 8-to-1. The length is 8 times the width of the rocket. That is a more racy, radical design. That would be considered almost an SSTO motor. You want to be very, very careful if you're going to develop those because they have a longer burn time. So you may need to think about nozzle cooling methods using halon or halon, some nitrogen or some other type of cooling materials. Because if you run hot exhaust gases through a nozzle long enough, depending on, actually not depending on when it's made, you can end up liquefying the nozzle and blow the purpose of the motor to begin with. So, and expend fuel in seconds and not minutes. A conservative design for a rocket motor is 6-to-1. 6-to-1 means the length is 6 times the width of the rocket motor. So this rocket motor would be considerably shorter, but you could divvy it, cut it in half, and then cut it in thirds on both sides of the half mark. That would be 6 segments to 1, including the bulkhead, which should also be a 4-square barrel. The length is equal to the width. Okay, and that may or may not contain a delay grain. But we're just talking about motors with no delay grain, where you're going to use electronics and pyrogen to separate the rocket halves and push out the drogues and regular parachutes. And of course, you have to account for the nozzle itself. A conservative rocket design, the only type of design I'm going to encourage is where the nozzle barrel itself is entirely inside the aluminum tube, and in itself is made up of material that does not transfer heat to the casing of the rocket motor itself. Very important. We'll talk about that more later. 6-to-1 is a relatively moderate performance rocket motor, depending on the fuel you use, depending on the weight of the rocket. You could have a flight from anywhere from 5 to 10 seconds on a 6-to-1. And 8-to-1, you can have a flight that lasts as long as 20 or 30 seconds. You have something that burns like that, depending on the size of the rocket, its design, the propellant grain, the nozzle, the materials you use. You can get altitudes of up to past 25, 30, 40,000 feet. That's serious high-powered rocketry. And a lot of people do that, but they know what they're doing. They have plenty of experience, and they have a lot of resources. And you usually have support teams where there's more than one person helping them out with designing, engineering, and building aspect of the rocket, the ground support equipment, support on the site. So they have people, like usually groups of 5 or 10 people, supporting a rocket that'll get altitudes above 30 or 40,000 feet. So SSTO motors tend to be radical design, 12 to 1, 12 times, the length is 12 times the diameter of the rocket motor. SSTO motors are entirely different. SSTO stands for single stage to orbit. There's no staging. It gets the rocket vehicle, the launch vehicle, into orbit without any of the segments of the rocket breaking apart and igniting another rocket motor. It eliminates a lot of complexity and moving parts. However, it creates other challenges, mostly being the temperature regulation of the exit nozzle itself, which is, where the business end of a rocket. How do you keep the temperatures down in an exit nozzle? Well, even I haven't perfected SSTO motors. I've barely launched a few of my own custom rockets, and I'm still playing around with rocket motor designs myself, but I know the basics, and that's what I'm teaching you. So anyway, we've got the rule of threes in review for the fuel grain design. We've got the rule of threes for the nozzle design, the nozzle barrel, and we've got the rule of threes for the head end design for a basic high-powered rocket motor. We've also got, which is ridiculous, I got to learn how to write backwards because the camera is recording me backwards. We've got the ratio for the length of rocket motor. We're going to concentrate on a beginner's luck type of motor, conservative design, rule of threes for the fuel grain, rule of threes for the nozzle and head end segments, conservative materials, conservative, established, successful propellant formulas, and of course a 6-to-1 ratio of length. Now, I want to talk about one last thing, and I'll let
power on.
Uh-oh. Okay. Oh, no, I'm sorry. That was my. Oh, thank goodness. That was my. That was my. I don't know why the hell that turned off. Okay, so we're not paired to the Bluetooth speaker. Worried me. We're at the 32-minute mark, and I've got to tell you, I guess we're going to go into overtime. So we discussed rocket motor length ratios. We discussed nozzle ratios, rule of three, three not square, but 3 times 2. And then we've got the ratios of length. I just want to discuss the ratios a little bit more. There's a 4-to-1 and there's a 3-to-1. 3-to-1 ratio is the rocket motor is 3 times in length than it is in its diameter. Those are very, very conservative rockets. That's sport rocketry, and you can make a 98 millimeter rocket motor that's very powerful that burns no more than 2 or 3 seconds and still gain about 8,000 feet of altitude. I don't really consider those a whole lot of fun. You're going through a whole lot of work for about 1 or 2 seconds of ecstasy. To me, I don't really see the point of that, but you might want to consider a short test flight for an experimental design airframe, so you might want to do things that way. So 3-to-1 is the minimum. You can go to 4-to-1, a little bit more flight time. 5-to-1, that's an oddball, but you can do that too. 6-to-1 length to width ratio of a rocket motor. That's where you want to start. Now, there's a power to weight ratio that applies to every moving vehicle that we have to consider with rockets airframe versus the total impulse of the rocket motor installed and designed for that rocket airframe. And total impulse being burn time times total times pressure and volume of thrust. You multiply those two, you get what's called, I keep forgetting this because I'm senile. You get what's called total impulse, TOTALIMPULSE, total impulse of the rocket motor. Okay, so, and then 8-to-1 is for your higher altitude to high power experimental rockets, where you're going to lose sight of the rocket even if you put flashlights, even if you put neon lights on it. And I don't recommend high altitude launches at night. I recommend them in a clear sky. High altitude launches, you want to paint your rocket black. And put neon smoke pot tracers on it for it to work in tandem with the recovery system, which we'll talk about later. Bright neon parachutes. Put a GPS in it. Put a black box in the electronics. The black box will record the events and serve as a heavy-duty backup in case the rocket crashes. You experience a CATO. GPS is a transponder that'll correlate with your smartphone. You don't need anything else but a program, an app for GPS, and then you can locate your rocket, which after it's attained a high power altitude of 40,000 feet, you probably could be traveling up to 10 or 20 miles to recover that rocket, depending on when you allowed or timed the delay to eject the parachutes. You don't want to do it too late. It'll reach terminal velocity, it'll tear the parachutes and the cord off. You do it too soon, you'll be chasing that rocket for 10 or 20 miles. And who knows where it's going to be. It might even end up in somebody's backyard, depending on where you launch it, because 20 miles is a long way. That's how it goes. 40,000 feet is roughly a little less than 7.5 miles. So that's a long ways. So be careful with that. Okay, there was one more thing I was going to talk about. The propellant formulations I'm not going to discuss. I'm not going to discuss that for a while, probably about 6 months. I have some other things going on in my life, and I want to be very diligent about getting those things taken care of. I have to make an important phone call after this video, after I upload this video. Now I am forgetting what it was that I was going to discuss. But nozzle cooling systems for a more advanced motor design. There was something else, but you know what? We're at the 30-second minute mark. This is the longest video I've ever recorded. I'm not sure. Well, I think YouTube will accept it, but I have some ideas for motor design. There was something else that was really important that I was going to discuss. But I do want to tell you this, and parting thought, we'll probably end up going to about 40 minutes on today's video. When you design and build your own rocket motors, set up the facilities to where everything is concrete and stone. It's cool, dry place, plenty of ventilation, nothing can catch fire. Wear protective gear, wear eye protection. Do not attempt to do anything with a rocket motor without wearing eye protection. You want to protect your ears, wear earplugs. If you have gloves or anything, that's fine. The best thing to do, though, is wear a smock, a machinist smock. Not mechanics, but machinists, they have these aprons that go around them. You can usually get a cotton smock at a painting store for about $25. And that thing is going to be your best friend when you're machining and tooling anything from the airframe to the rocket motor assembly itself. Mixing fuel propellants, like I said, I'm going to hold off about 6 months on that. That is very, very dangerous. But I just want to tell you, if you're going to be cavalier about it, be careful. Make sure in a cool, dry place. Research rocket fuel propellant formulas. You can get anything and everything you want off of the internet. Don't go on YouTube. You can just go on the regular internet, Google Chrome, Microsoft Edge. There's DuckDuckGo. There's even Firefox, which used to be my favorite. Firefox has a variety of different search engines. Set your browser settings to private. You don't want other people knowing about your browser history. If you have evil intentions or you're malevolent about this, this information is not suited for people who want to do destructive acts that would constitute terrorism. I denounce that wholeheartedly. I don't like that. I'm a white bread American person. That's third hairstyle. Yeah, can't paint a barn. Paint keeps falling off. But I denounce violence in any forms. I'm a designer. I am an engineer. I'd like to be a scientist. I'm working on my MBA, University of the State of Colorado. I've got to get on that as well. I've got a lot of affairs I have to tend to in my life. Unfortunately, in Orange County, it's a very, very expensive place to make a living. So that is an official complaint, not political, it's more economic. Let me scratch my back because I got an itch. But anyway, that's pretty much that. So we talked about the rules of threes, and I didn't know I was going to get into this. I thought I was going to be talking about something else. Tomorrow's episode, we're going to talk about launch support equipment. We talked a little bit about motors today. I've got to be honest with you, I've enjoyed myself talking about rocket motors, but I didn't want to get into it this soon. We're going to talk about something that I've listed on OfferUp. It's a 5-channel launch controller. and we're nearly at the 40-minute mark. So I've got to cut it because it's going to take all day to upload onto YouTube and to take up all the memory on my phone. So I got to say goodbye. Um, Now there is, if you can see her, that is Valencia, and she's been cooing all night looking for a boyfriend. Don't ask, I won't tell. Paxton is right there. Paxton is a boy; he's not a girl. So, and so they own the place. It's really their operation, not mine. Cats that go into a house, they automatically own the place because they're cats. Anyway, my name has been Jason. My name is Jason Wampler. I've been your host. I'm the one who designs, engineers, and builds and explains all this stuff because I figured it out on my own. I've been building rockets for 23 years, and this has been another installment of the Rocket episode, or excuse me, the Rocket Minute. Hit the like button, hit the subscribe button. Please give me any and all comments you can. It doesn't matter how negative or positive they are. I want to hear everything and anything you guys have to say. Actually, you girls too. I'm in a process of a marketing campaign to get more interest from the lady folk, from women in rocketry. I think it's an interest that lies dormant with the women in this world only because of certain things that women experience in regards to input from other people and stigmas and things that hang-ups that modern Western society has that I don't really particularly care for. I'm not going to get into it. Anyway, this has been another episode of the Rocket Minute with your host, that's me, Jason Wampler. An Armstrong Media production, but like I said, Paxton and Valencia, they actually own the place. Thanks a lot. Thanks for watching. Hit the like, hit the subscribe button. I want to monetize. I need to make money. Bye.